Why, hello everyone. So we'll be spending the next 40 minutes or so on a topic that's been on my mind and my area of interest for a while now, which is the impact of AI and quantum computing on cybersecurity. I'm always trying to kind of keep up with the latest trends and see how that will affect my work in the years to come. And this is as much as I could kind of cram into 40 minutes of presentation. So my name is Tudor, Damian. I'm here for, I think, the 8th time at DefCamp. It's so great to see the event evolve over the years. It's amazing to see all the people that are interested to find out about all these new trends and interesting topics. I've had a lot of awesome conversations over the past day and a half. As was mentioned, nowadays I do cybersecurity with a company called D3 Cyber that I co-founded. For the board gamers in the room, I've also got kind of a hobby turned business in Cluj. It's an amazing space where you can go check out, play board games and things like that. I've been a part of this year's first edition of DefCamp in Cluj-Napoca. Anyone here who's been to DefCamp in Cluj? Oh wow, so quite a crowd. So without further ado, you're not here to listen to me talk about myself. The overview of the agenda for my talk, I'm gonna briefly touch on AI. I don't want to go too much into detail on the AI side. There's already a lot of topics out there, and if there's anyone in this room that doesn't know about ChatGPT or what's been going on lately, I think you're in the wrong room, right? I will spend some time, though, on the quantum computing side and looking at how that will impact, especially the stuff about encryption, and I will be touching a bit on privacy-enhancing technologies that kind of tend to help on both ends of the spectrum, so both with AI and quantum. So yes, if we look at cybersecurity today, you've probably heard this more than once over the past day and a half. There's a huge increase over the past few years in both the frequency and sophistication of attacks. They're getting more and more frequent or more and more visible. Maybe they were frequent before, we just didn't know where and how to look. And the rapid change of pace of technology and of the tools that the bad guys have at their disposal far outpaces what we're able to do to counteract that, or even if we are to look at legislation. Here in the EU, we're, I think, one of the best positioned regions in the world when it comes to legislation around cybersecurity. Think about GDPR and privacy, think about NIS2, think about stuff like DORA or the CRA that was just mentioned. But even those things come into effect years after they are actually needed. So even on that front, we're still kind of lagging behind the technology itself. The AI Act is also something that's coming in the EU as well. And there's a clear need for more of what's called adaptive security. So sort of a shift from trying to just react to what's being thrown at us to what we discover that's going on and try to prevent or predict and try to better act in a way that we can better handle the unknown, the black swans of cybersecurity events, right? So in that respect, AI is one of those areas where a lot of changes are happening really, really fast. And some of those changes might be too fast for some, right? When it comes to the impact, the positive impact of AI in cybersecurity, obviously you've got automated threat detection. Nobody has the time, resources, and energy to look through logs manually, right? To monitor network traffic manually, to look at behavioral analytics, to try and figure out in huge amounts of data being thrown at us that there's a user that usually logs in Monday to Friday, 9 to 6, from the office or from home through a VPN, and all of a sudden they've connected from Russia on a Saturday at 3 a.m. and they're accessing servers and resources on the network they don't usually access. That kind of behavior is something that should be identified as soon as possible, because Monday morning, 9 a.m. or 10 a.m., when the IT team wakes up, decides to log in and check any notifications, that might be too late, right? So you do have the automation and the large-scale machine learning and all that stuff that's obviously helpful. Also on the incident response side, again, responding on a Monday morning to an alert, instead of having some automated system kind of disable access for that user or force or trigger another MFA authentication just to validate that they are who they say they are and it's not just a compromised account, if you will. That's also part of where AI has been helping a lot in recent years. However, we do have the dark side of AI, if you will, with adaptive malware that is now more and more able to adapt and to change in a way that makes it harder for these automated systems to detect that there's malware going on. The Nigerian scam emails now are written in perfect English. No longer do you have typos, errors, like spelling errors, and they get translated in many, many different languages now because of AI, right? You've got these tools that help you better translate and better localize your phishing attacks. Deepfakes have seen a huge increase in recent years, and we'll touch on that in a bit. And now you've got AI tools that are designed to find weaknesses better, faster than what traditional tools, if you will, are able to do. You've also got adversarial attacks on AI systems, trying to break those AI systems so that they don't do as good a job as they are supposed to be doing. So going back to the previous slide with AI trying to help detect these things, if you can trick that system into maybe marking something as a false positive or just ignoring it altogether, you're golden. And then, of course, you've got all the data privacy concerns, which we'll, again, touch on in a bit. So I've got a quick video on right now, and this should have sound as well. Yep. So this is one of the many examples just the Door Brothers account has on their account on deepfakes. So they've got a whole bunch of these. I just picked one. The thing is, synthetic media has been an issue, and it's getting harder and harder to distinguish what's fake from what isn't. We're long gone from the days of just fake news. Now it's easier to fake photos or videos of somebody else in their own voice saying something that you want them to say. And for people to just take a quick glance and figure out this is fake, instead of should I be able to tell it's fake, or just I don't care if it's fake or not, I heard it on the news, it's on the internet, so it must be true, kind of a thing. Once one of these things makes its way into the people's kind of reach, it's harder to dismiss any claims, anything that pops up on X, right? Formerly Twitter. Yeah, they do have the community notes there. Who reads that? Once something gets retweeted a million times, nobody bothers to go back to the same tweet and see, this is fake. This is false information. So in this area of fake news, you've got the whole new level that generative models can bring. And deepfakes for the past 4 years have been growing 900% year over year. And this is not stopping. And again, this was just one example. There's some potential solutions around deepfakes and kind of AI-generated images for people and companies and media outlets to be able to kind of tell if they're real. These are some areas where there's investments being done. It's not an easy solution, but even the likes of Nikon, Sony, and Canon are looking at embedding digital signatures and PKIs into their cameras and digitally signing the pictures that you take with one of their cameras to ensure that it's not being tampered with, for instance, right? Or you have the AI-based deepfake detection, which is all about that adversarial thing. You've got AI detecting AI, so you need the other AI to get better at not being detected, right? Digital watermarking, and this is something that Google's been playing with, content credentials as well, providing some metadata with the file to prove the origin and that, again, it's not being tampered with. There's a whole bunch of these examples out there of AI manipulated attack. One of them, you might have heard of it, it's from earlier this year, where a finance worker paid out $25 million in a bogus account, a malicious account, because someone who claimed was their CFO got on a video call with them, and it was a real-time deepfake of their CFO with his face, with his voice and everything, telling them, pay the $25 million in this account. And this was from earlier this year. So it's harder and harder to kind of tell, because you're on a Zoom or Teams call with that person, and they're telling you, yeah, do this. And you're gonna, yeah, well, if he told me, and I know him, and I've heard his voice, and I've seen his face, it must be him, right? And there's no way to tell. There's been an increased use of AI in cybercrime. Ever since ChatGPT was launched, and back then it used to be called Opune AI, everything you could do with their model that has since received some restrictions in what it's allowing you to do. There's a bunch of others though, and they're just a quick search away. WormGPT, which has been since shut down, this was a tool used to launch sophisticated business email compromise attacks, right? Helping you launch those attacks and formulate the emails and everything using a tool. FraudGPT and BlackHatGPT, they are designed specifically for malicious activities like creating malware, finding vulnerabilities, and things of that nature. Or if you now have trouble getting ChatGPT to give you that exploit script, there's a jailbreak as a service right now called EscapeGPT that allows you to escape the restrictions that some models put on, because you saw the video before. That kind of video is generated with models that are not as restrictive, such as Elon's Grok and a bunch of others. That if you tell it, create a picture of, I don't know, Obama holding a gun or shooting at somebody, and they'll be, yeah, of course, here's an image of Obama holding a gun shooting at somebody. So if you want to escape those models, there's ways to do that. Now, on the other side of the spectrum, and this is where I'm going to kind of wrap up on the whole AI thing, let's touch base a bit on the quantum computing side, because this is, I think, where things will get even more interesting in the upcoming years, and I think it's going to be coming sooner rather than later. Who here has been to Chris's talk yesterday morning? Okay, so not a lot of you. Cool, there's not a lot of overlap, but there's been some talk of quantum there as well. Are you guys familiar with logic gates? You work in IT, right? This is a very good example of how logic gates work in relationships. Where you've got, of course, it's cryptography, so you've got Bob and Alice, right? So if Bob is wrong and Alice is right, the result is, of course, Alice is right. If Bob is right and Alice is right, so if they're both right, obviously Alice is right. If Bob is right and Alice is wrong, obviously Alice is right. And when they're both wrong, then Bob is wrong, right? So in a traditional computing, this is what you are probably familiar with when you work with bits, with 0 and 1 or 0 or 1, the XORs and everything. So this is probably familiar territory for a whole lot of you. For those who aren't, this is what you're getting yourself into if you want to try IT, right? And understanding what you're doing, or at least hoping to understand what you're doing. When it comes to quantum, though, things are a bit different. So up until now, we've been kind of getting accustomed to using zeros and ones, right? And anything that's a bit, it could be a 0 or a 1. And transmitting data from one place to another, it's transmitting these strings of zeros or ones, and it's 0, 0, 1, 0, 0, 1, 1, 1, 0, and that's all that's ever been when it comes to computing in the end. With quantum computing, things change in a radical way. You've got now what are called qubits, and a qubit is sort of like a fancier version of a bit, because it can be a 0, a 1, or anything between a 0 and a 1 at the same time, which might be harder to comprehend because quantum physics is not like stuff you learn in kindergarten for a reason, right? So a qubit can be a 0 or a 1 at any given time, and it's all about the probability of it being a 0 or a 1. That's how it kind of works. And it's usually represented as a sphere, where the very top, think of this as the globe. Sorry for the flat earthers in the room. Think of this as a globe, right? The North Pole is a 0, the South Pole is a 1. And then you've got the latitude, which is degrees of zeros and ones. If you're on the equator, it's a 50% chance of that qubit being a 0 or a 1. If you're further north, like we are now, it's kind of a, like, say, 75% chance of this being a 0 and 25% chance of it being a 1. And then you've got the longitude, which is the phase. Now, I'm not going to go into a lot of details here, but it's wave functions. And if you combine waves, and that's valid for anything that's a wave, with sounds and things that are wavy, right? If you combine them, you get a peak that's higher. If you've got a wave at the same kind of frequency, you can have hills and valleys, and if it's a hill on one and a valley on the other, they cancel each other out. If it's both a hill, they add to each other, kind of a thing. And that phase is represented by the longitude on the globe. Now with this, with qubits, you've got a whole bunch of other things that stem from quantum physics. One of them is superposition, which means, like I said before, qubits can exist in multiple states simultaneously. And it's only through observation, through the act of observation, that you collapse the wave function, and that thing becomes a 0 or a 1. But up until you observe, it could be anything, with a higher or lower certainty, probability, if you will. But it's not a 0 or a 1 until you observe it. And up until that point, it could be anything. It's like Schrodinger's cat kind of a thing. Entanglement is another thing where you could have qubits that are interconnected and they affect each other's state instantly. Think of it this way. If you roll a die on Earth, right, and you roll a 6, and you've got another die that's entangled with it, that's on Mars. That die on Mars will instantly flip on the 6th side. That's entanglement. If you change the state of one thing anywhere in the universe, the entangled particle, wherever that is, will instantly flip to the same state. And that's what, again, the magic of quantum physics and everything. And then you've got quantum gates, which is a huge shift from traditional logic gates, but it's how you would affect these qubits, how you would change their state, wave, function, probability, and everything. You do it through these quantum gates. These are the building blocks of quantum computers, of quantum circuits. Anything that allows you to change a bit from one potential state to another would go through one of these quantum gates. It's stuff like rotation, inversion, entanglement, things of that nature. This is how you do it. And then another aspect is about decoherence. Because one of the biggest challenges in quantum computing is to bring this to the physical space, right? And maintaining that quantum coherence, that thing where things are quantum, right? And you have to do it and you can usually do it in many different ways, but some of them involve stuff like close to 0 Kelvin temperatures. Absolute zero, so that those particles behave in a quantum way and you can measure them. So if you have the index telling you how much decoherence can happen with a system and how long it will take for it to lose its quantum properties, that's how long that quantum computer will be able to be quantum, if you will. So there's, just to kind of go over the basics again, if you imagine a coin as a bit, and you flip that coin, if it's heads, it's a 1. If it's tails, it's a 0. With a qubit, it's a 0 and 1 at the same time, thanks to the superposition. And think of it as the coin while it's spinning. You don't know if it's going to be a heads or tails until it stops spinning, until it falls on the table, on the ground, wherever, and it stops with the heads face up or tails face up. With a coin, that's kind of a 50-50 chance. Again, the people that don't understand this are the people betting on stuff or playing at casinos, right? But with a coin, it's a 50-50, right? With a qubit, it's anywhere between 0 and 1 based on multiple factors. But until the coin stops, you don't know if it's a 0 or 1, thanks to the superposition. With 2 bits, in traditional computing, you can have 4 states. Those 2 bits could be a 0, 0, 0, 1, 1, 0, or 1, 1, right? With 2 qubits, you can have all 4 states at the same time. It's not that one or that one or that one or that one. It's all of them at the same time. So the more qubits you add, the amount of states that system can hold increases exponentially instead of just with traditional bits. And that's why quantum computing can be so difficult to do, but also can have potential huge implications. I won't spend too much time on this, but this is how the quantum gates look like, right? If you want to look into this, you need to kind of understand a little bit of math, a little bit of quantum physics, but this is kind of different from what you were accustomed to with the traditional logic gates, right? Now, there's obviously a huge positive impact that quantum's bringing. One is around optimization. So anything that relies around finding the most efficient route for logistics, like the traveling salesman problem, for instance, which is very hard to do with traditional compute resources, but with a quantum computer, you try to define the end state you want to reach, and you let the qubits in the system figure it out on their own, and by the time they collapse, you find the solution. Now, this is oversimplifying it, obviously, and again, far too little time for us to go into any details, but it is about optimizing known traditional compute-intensive problems. Also accelerating the discovery of new drugs, new medicine by simulating all the interactions between the molecules, for instance, which is stuff that's harder to scale on traditional computers. Improving weather prediction, because you can kind of simulate these systems at scale and all the intricacies and all the interactions between the dynamic systems that are involved in weather patterns, for instance, or financial optimization. So there's a lot of areas where quantum could help. There's a whole bunch of ways in which this can be physically implemented, and you've probably seen one of these things in pictures when you read an article about quantum computers. There's a bunch of these things that have been going on in recent years. One, superconducting qubits. This is the superconducting circuits cooled to near absolute zero. And an example of this is Google's Sycamore processor. Trapped ion qubits, which is a solution that has higher coherence time, so it's less susceptible to decoherence, but it's harder to scale to larger number of qubits. This is what IonQ is doing, for instance, if you've heard of them. Photonic qubits, where it uses the properties of photons, such as polarization, and these things can operate at room temperature, but it's a challenge to scale them for large-scale implementations of multi-qubit gates, so they work for smaller size qubit numbers. Spin qubits and quantum dots, so there's a bunch of these. Again, if you want to look into it. I've got a timeline that I was curious to see where things are going, right? And if you were to look at late 80s, 90s, early 2000s, you usually had just theoretical developments of these things. Of course, yeah, granted, in 1998, we had our first 2-bit quantum computer demonstrated, but that was about it. And then for a long time, nothing really happened until 2017, when IBM, one of the leaders in this qubit space, they introduced Qiskit, which marked the beginning of the practical computing effort. This is a quantum computer built with their framework, had 5 qubits, and if you could afford it, you could also try it out. Right? They had ways in which they gave access to any company that wanted to try it. And then that grew. Like 2020, you have IonQ achieving 11 fully connected qubits. Then 2021, it's IBM again with 127, and then 433, and then comes atom computing with over 1,000. Earlier this year, D-Wave had a computer that started with 1,200, and it's this month that they announced that they reached 4,400 plus. IBM also announced that next year they're going to be bringing their own thing. What I wanted to show here, this is how the graph looks like. Right? So this is the current trend of the number of qubits in systems, and this is what's harder for people to grasp as far as the rate at which quantum computing is evolving. Because this thing is not going to stop, right? It's going to go way, way higher, and the impact might come sooner. Now, when it comes to quantum, you've got the whole other side of the discussion with post-quantum cryptography, which is a shift in the way we do encryption, for instance, right? And the way right now, the algorithms that are used to encrypt stuff, they're based on mathematical problems that are believed to be hard for computers to solve in a reasonable amount of time, like factoring large primes, for instance. Quantum changes that. And you already have implementations in real life of quantum technology. This thing is a real device you can go out and buy. It's like tens of thousands of euros, but you can buy it, right? And this helps with quantum key distribution. So it transfers keys over a quantum channel. And because of the way quantum stuff works, if there's an observer, you know there's an observer. So it's physically impossible for someone to monitor the traffic because of how quantum technology works, because you would know that someone has monitored the traffic. So you would know that that key exchange was monitored. Someone looked at it, right? So this is how that technology works. Now, like I said, quantum computing does tend to break traditional cryptography, and it's stuff around integer factorization, which RSA depends on, or discrete logarithms, which elliptic curve cryptography depends on. And one thing that's in danger here is long-term data security, because there's this thing, and Chris talked about it yesterday, either store now, decrypt later, or harvest now, decrypt later. If I were to capture data, traffic of any kind today, data at rest, data over the wire, that's encrypted with current technologies, and 2, 3, 5 years from now, I get access to some quantum computer that allows me to decrypt that data in seconds instead of, I don't know, millennia, then that data is at risk. And yes, I agree, it's only at risk if you think that this data being decrypted 3 years from now or 5 years from now is a risk. But in those cases, you need to start thinking today how you're protecting that data, because if it's harvested or stored now and decrypted later when technology becomes available, it might be too late. And let's look at a couple of ways in which this can happen. There's a couple of algorithms, and they're quite famous if you've looked into the whole post-quantum cryptography. One's Shor's algorithm, which is an algorithm that's able to easily break RSA and elliptic curve cryptography by solving the discrete logarithm problem exponentially faster than anything running on classical computer. And there's another one called Grover's algorithm, which does a search. So right now, if you've got a database of n items and you want to do a search to find an item, if it's unsorted, it can take you up to n steps, right? To find, if it's the last one in the table and you're looking one by one, it might take you up to n steps. With this algorithm, you can do the same thing in the square root of n steps. So that means that anything that's affected by that will just require much larger keys. It impacts symmetric key cryptography and hash functions, so you just need double the key length, double the hash size, and so on. And this is, maybe this is, if you want to take pictures or anything, maybe this is what you want to look. I know the slides will be published as well, so, and if you can't wait until then, you can just drop me a line and I'll send them to you even after this talk. But just looking at symmetric keys and one-way hashes, it's like larger key size needed or larger output. With anything such as PGP or GPG, with RSA, which is used in public key infrastructures, with elliptic curve digital signature algorithms or elliptic curve Diffie-Hellman or DSA, they're no longer considered to be secure when it comes to using quantum to decrypt. So this is what we're looking at. So what's the solution there? Well, NIST has started, back in December of 2016, what's called a post-quantum cryptography initiative, where they try to figure out if there's some algorithms they could use to make cryptography better or more resilient when it comes to quantum computing. By the 2017 deadline, they received 69 candidate algorithms. They filtered them out. Some of them were selected for further analysis. Last year and earlier this year for Falcon, they have selected 4 of these that they consider to be quantum safe. And they've started the process to standardize them. So you might expect to, and some of them are already available in some encryption libraries today. But if you've got a standard, it means it's going to be easier to find them in systems that you use today. You just make sure that you use these instead of the old ones now, if you will. There's also a open quantum safe project that has stuff around VPN, TLS, or SSH, basically forks of OpenSSH or OpenSSL or OpenVPN that have started to integrate these things, these algorithms into the mix. And there's a whole bunch of other work done around PQC. Again, I'm not going to go into details here, but if you're a math geek, this is certainly your space. This is also where they found some stuff that looked promising in the beginning, and they figured out, nah, you can break this in minutes or hours, actually, like Psych, for instance. That was a good example. So let's look for a few minutes at PETs, or privacy-enhancing technologies. So these things are tools and methods that are designed to protect user privacy in the current age of big data, of machine learning, and AI. And I kind of cherry-picked a few examples, such as homomorphic encryption, secure multi-party computation and differential privacy, and trusted execution environments. So homomorphic encryption is all about doing computations on data while the data is encrypted. So how does this work? It's you get a number, you encrypt it, you provide the encrypted result to somebody, like a cloud provider. They do something, mathemagics, if you will. They do the computation on the data that's encrypted, so they have no clue what they're working with. And they give you the encrypted result, which you decrypt with a key that only you have, and you get the actual result. But this means that whoever's doing the computation never actually knew what data they were using to do the math. And there's three ways in which this can be done. One's partial homomorphic encryption, where you can do just one type of operation. You can either add or multiply, but you can do that an unlimited number of times. Then you've got somewhat homomorphic encryption, where you can do both addition and multiplication, but you can do it a limited number of times. And then you've got the holy grail of HME, which is fully homomorphic encryption, which does both addition and multiplication an unlimited number of times. Now, this means you can do anything, because, you know, if you add a minus, you actually subtract. If you multiply by a fraction, you actually, you divide, right? So addition and multiplication is all you need. So this means that you can do this at scale. The challenges of this, you've got computational overhead, because a huge amount of compute power is needed to do these things that you could otherwise do without using encryption. It's complex to implement, especially fully homomorphic encryption. That's really hard to implement. And you've got huge data size needs, because you need to store all the encrypted stuff, and it takes a lot more space in memory or on the disk than it does if the data is not encrypted. But it's a thing. Now, with secure multi-party computation and differential privacy, I'll leave you guys to discover this on your own. The essence of this is you can either have multiple parties compute something without each of the parties revealing the individual data that they use. And I've got, I think I've got a couple of examples. Like banks doing collaborative fraud detection. They want to figure out if there's some fraud happening, and you've got some accounts in your bank, and I've got some accounts in my bank. I don't want to share any of the information, like you don't want to share. But we're looking at transactions, and we figure out that there's something weird going on with a particular account. We figure out what that is, but at no point during this interaction have I given you a list of my accounts, and you've not given me a list of your accounts. But we were able to compute this together. Or medical research across hospitals, like doing a calculation on the number of patients with a rare disease without actually sharing information about the individual patients. When it comes to differential privacy, this is doing large-scale statistical analysis without revealing or having the potential to reveal individual data, right? And where this could be used, things like secure voting systems, right? You could have a system where anyone can vote, but you will not know who each person voted with, right? Stuff of that nature. Secure data processing in the cloud. Having a cloud provider do mathematics on your data without having access to your data, doing it encrypted. Privacy preserving data analytics. So I'm not giving you information about the individuals in a study. I'm adding some randomness, but it's controlled randomness, so that you can tell who's who, but you can still do relevant statistics over the data set. Like, you can look into this. I don't have any hope that my 2 minutes will help you understand all of these things. I'm just trying to help you know that they exist, maybe. And let's look at kind of a wrap-up here, a roadmap for the future. How can we address these things? Well, start with a zero-trust approach. Verify everything explicitly. You shouldn't trust anything just because a user has logged in with a valid password, it doesn't mean that it's that user and it's not someone who's hacked their account. Use a least privilege access approach anywhere, like just in time, just enough access, and use an assume breach approach. Start thinking, what if I've already been hacked? How can I detect that instead of thinking, how can I prevent getting hacked, right? So this is one step. Think and look at the evolving threat landscape. Yes, you need to adapt because things are changing quickly, so if you're not familiar with those things, you won't know how to start looking at implementing them in your infrastructure and in your solutions and applications. Transitioning to new algorithms and new solutions because some of the existing ones might be unsafe in a few years or even a few months. And designing systems that are compatible with both current and future standards. Implementing AI-driven tools, investing in quantum-resistant solutions and figuring out what that means for you and where you need to put that in. Start looking at those pets I mentioned before because they're there right now. They're available today. They're solutions and technologies that I think not enough people and companies use them because most of them don't even know they exist. And they could help a lot. And of course, staying on top of things. So with this, we're almost done. If you want to try out quantum today, there's a bunch of resources out there. All of the major cloud providers have their own quantum thing with libraries, with pieces of code that you can start using today, stuff that you can try, helpful communities, resources, and so on. And it's becoming more and more affordable. You don't need to build one of those systems in your basement and keep everything cooled at 0 Kelvin when IBM and Amazon and Microsoft and Google are doing it for you. And you can pay a much smaller fee per minute or per hour to try them out. So in essence, and wrapping things up, AI and quantum do present both opportunities and challenges. And just evolving any cybersecurity measures that you implement becomes an obvious need. Staying on top of things, embrace these things responsibly, and get involved in anything that has to do with keeping up to date and addressing these challenges. Now, I don't know if we've got time for Q&A. I am available. I am around, so we can talk even after the session. Thank you.
Thank you very much, Tudor. We can allow a couple of questions. Any question? I see it here in the front.
Here.
Thank you. First of all, it was a great presentation in a short time. You covered a lot of topics, and I just wanted to understand what is the connection from quantum computing and privacy-enhanced technologies, pets. How you see that relation, connection?
Well, so in some cases, usually pets and most stuff around cybersecurity involves encryption. So figuring out a way to use privacy-enhancing technologies, but with encryption that's, say, quantum safe, for instance, that's the way to go, trying to make this all fit, trying to figure out how you can properly use AI, how you can properly implement any available quantum safe algorithms, how you can start to better encrypt your data in ways that you probably haven't done before. Like I said, pets usually have to do with cryptography. Cryptography is threatened by quantum, so that's where the connection is.
And maybe using quantum computing to do the computation savage needs for pets. So homomorphic encryption based on quantum computing.
Yeah.
I said yeah. Thank you.
And there's huge research being done in that space, and people are still trying to find more algorithms that are quantum safe. But it's a long work, and when they think they found something and then somebody else comes up with the research, like, again, just look Psyche, S-I-K-E, and they show that, hey, you know this thing that you said it's quantum safe? I can show you how you can break it in minutes or hours, right?
Thank you. The second one in the second row, the second part of the room.
So you talked about quantum and AI.
Yep.
And if we were to combine the both of them, how would it actually affect, for example, the job market? Because some jobs can be made almost, some problems can be solved instantly with the use of AI.
So that's a very good question and a very dear question to me. Whenever I talk, and I frequently interact with even students in my former university every year, I've got guest lectures there. The thing is, with the way things are evolving, it's hard to think today what are the jobs that will be available 10 years from now. Many jobs in IT today did not exist 5 or 10 years ago, right? If you are preparing to be a social media specialist in 2005, nobody knew back then what Instagram and TikTok and Facebook were, right? So it's hard to try to predict how this thing will change, especially given the rapid pace at which we've already seen this technology impact current jobs. Like in the past just 2 years alone, with the advent of ChatGPT and the like, some jobs have become less relevant or have shifted towards, hey, if you can make AI work with you, you're going to be able to keep your job. If you're adamant about not using AI in your job, then maybe we should be looking for somebody else. We're not at a point where AI replaces people at scale in their jobs, but we might not be far from certain jobs being replaced, right? Right now you've got taxi drivers feeling threatened because of solutions in the States where you've got self-driving cars in a taxi company, right? Next is going to be truck drivers and things of that nature. So it's hard to predict. The most certain thing about IT is uncertainty, right? So just expect the unexpected, prepare for stuff that you can't even prepare for. And if you are able to accept that you're going to have to be constantly learning your entire life if you start working in IT, then you're good. My recommendation, just look at Nassim Taleb's Incerto series, things like Black Swan, Anti-Fragile, and that stuff. He talks about how to kind of try to prepare for the unexpected, because you can't predict something that you can't know might happen, but there's still ways to become anti-fragile, if you will.
Here.
All right.
Firstly, congratulations for your presentation.
Thank you.
So, you've mentioned that the cyber incident response process has been automated with the help of AI. But
some parts of it.
Yeah.
Some parts of
the
it.
mitigation part.
Yes.
But what's your opinion? Could AI fully replace in the future the cyber incident responders or the cybersecurity analysts?
The less prepared ones, yes.
Indeed.
So I don't think in the near future it's going to be able to replace everyone, like I said. But if you're not bringing that much value, then yes, you might start to feel threatened that AI might take some of a part of your job or your entire job soon. There's still a huge gap in terms of what AI can actually do, and a lot of people don't understand that these LLMs, these large language models, are exactly what it says, language models. And if you tell ChatGPT that what's 2 plus 2, and it tells you 4, and you say, no, it's 5, and it tells you, yes, I'm sorry, it's 5, right? It gives you what's statistically probable to sound good, but it hallucinates and does all those things. Granted, there's other models that are better designed for that. But again, we're not there yet, and there's still a long way to go for some of these things to be fully replaced. I believe in an AI-assisted world where you've got AI doing the boring parts for you, but you still need to be able to understand the output. And you should be able to generate that output on your own. And then when you ask AI to do it for you, you can validate that what it did is correct, it's okay, instead of not understanding and asking AI to do something that you don't know. That's where the risk is, and that's where the main problems are today.
Okay, thank you.
No problem.
When you were talking about generating deepfakes, when quantum will be more available and it will do this, the deepfakes will get much better. And my question is, how will we detect this? Because, for example, when Apple was developing their AI editing for their computers and phones, they were adding some metadata to the image to mark it as edited, but it could be simply removed and the image would look like it was original and was never edited.
Okay, so one thing about quantum is it will not change everything. So there's certain areas where quantum computing will bring enhancements, but it's not going to be everything. And right now, I don't know of any kind of work being done or algorithms helping deepfakes be better, faster, and harder to detect. It doesn't mean it won't happen, but the way quantum technologies help is if you understand how quantum physics works and what qubits can help you do. And deepfakes is not first on the list there. So there's areas where quantum will have zero impact in terms of processing power, in terms of, I don't know, impact of like making things faster or better. I'm not sure if deepfakes is one of those areas or not. I know there's some areas where it does have an impact. I've listed some of them on my slides.
One last question we have here in the front.
Hello.
Yep.
First of all, great presentation. I wanted to ask you, you have spoken about quantum computing and cryptography, and I wanted to ask you that if quantum computing will bring the profitability of Bitcoin mining back.
They're very different things. And right now I don't see how that thing might impact, because just building a quantum computer is expensive. So using it to do Bitcoin mining might not be the best use of it. Again, it depends on how you start using it. Right now, there's very few algorithms and actual practical implementations of stuff that is able to use quantum. Now, if somebody goes out there and figures out a better way to do crypto mining using quantum and pushes out a library that you can use, then yes, crypto mining might be a thing that's faster and better using quantum. There's a lot of uncertainties because right now there's not enough people working on actual practical implementations on stuff that would use quantum. But now that you've got the physical systems themselves, this is the moment when those things start to happen. What's going to happen, again, I don't know if I can reasonably predict that. A lot could happen. I talked about stuff that's certainly going to happen.
Thank you.
No problem.
Thank you very much.
Thank you as well.